Hey, Adam, I missed last time around. Did we get to see baby pictures? Are we gonna get to see it?
I could grab this baby here. Let me ask first, do people see my screen, this full screen? Like the title slide?
Yes.
Okay, good. I'll show the baby at the end of the meeting if we get there. So right off the bat, I'm going to change this date. February 7th. And I cannot spell February. Yeah, but thanks for asking, Ken. The baby is doing well. Everybody's happy and healthy. We're one day of chaos and then one day where we think we have it figured out, followed by another day of chaos, and that's pretty much what it's been. But I've been taking the night shifts, so I'm like cobbling together enough sleep, I think. But it's I figured that like the choice you have to make is whether to get enough sleep or not. And if you want to get enough sleep, then you have to basically extend the duration of your night. You know, you have to be like, okay, instead of going to bed at 11 and waking up at 7, I need to go to bed at like 9:30 and wake up at 8:30. Because then you can take 3 hours in the middle of the night and like deal with everything. But I'm sure those who've had kids, you know, had their own strategies. That's just mine. So my days are effectively way shorter than they used to be right now. But you know, that'll last only so long, I'm sure.
That actually seems like a pretty low chaos ratio. So well done if you're actually maintaining every other day low chaos.
Yeah, no kidding. You know, we only have one kid. We're only gonna have one kid. And for those of you who have multiple kids, all I have to say is I've at times just imagined having like a 2-year-old running around in addition to an infant. And yeah, that's very scary. So I applaud all of you who have not only, you know, a kid, which is hard enough, but like multiple kids. I have more respect for you now than I ever did before. So, well, welcome everybody. We'll dive in here, and thanks for joining. Right out the gate, just a couple agenda topics, and I don't even have here on this agenda, but I wanted to introduce Lakis, who is with Recurve, and he is going to be helping provide logistical support for this working group. And I think I mentioned at the last meeting, we've had a few little snafus with scheduling, and like the Zoom links that we've been sending haven't, there's a bug in like the Zoom application where it's not connecting to people's calendars very well. So we're going to be switching over to Google Meet, which is what we're on now. And so sorry if that threw folks for a loop, but we're just trying to remedy some of these little snafus that have caused some confusion. And Lakis is going to be providing more logistical support. So we're trying to give some dedicated logistical support to this process. And so he's a good person to get in contact with if you're having trouble with scheduling or the invites or anything like that. Also, I believe if we were able to cancel the Zoom invites, but you actually have to remove those from your calendar. So if you have the Zoom invite on your calendar, you need to actually remove that yourself, which is awkward, but that's just the way it works, I suppose. So with that being said, thank you, Lakis, ahead of time for all the help, and thanks for Shay, who has provided logistical support so far and has done her best to manage all these weird Zoom bugs and features. So with that being said, we're going to start off today with a little bit of change of pace, and wanted to give a little bit of time and space for McGee to talk about Shulie Goodman, who's somebody who's been super integral to Linux Foundation Energy, and is, I think without Shulie, it's probably safe to say we wouldn't be here together today. And then we'll go into, you know, the meat of what would like to discuss today, which is just a quick review of the testing framework and kind of why we're going about what we're doing and paying so much attention to that. And then some initial results. I think we're starting to be able to run some of these preliminary models on population data. So we're getting a sense of where the optimization of all of this needs to progress. And so today you're going to see some, I think, exciting preliminary results, but also a set of results that clearly leaves some open questions, and we'd love to have some feedback on that. And there's definitely some areas where, you know, we're going to have a lot of work still lies ahead. Then we're going to have some discussion. I think we'll have more time today because we don't have quite as much like base material to get through, and then give some previews and thoughts on where we think some good testing should be devoted, some like good time and effort toward additional testing should be placed so that we can start to wrap our heads around and like put the stake in the heart of some of these questions that we're going to highlight today. So with that being said, McGee, if you don't mind, could I pass the baton to you to say a few words about Shulie and the opportunity to contribute to the Memorial Fund in her name?
Yeah, thanks, Adam. I'm saddened that this is my first contribution to the conversation, you know, in this working group this year. For those of you who don't know who Shulie was, she was the executive director of LF Energy, the founding executive director of LF Energy, and so, you know, the connection for this project, you know, technically now this is the OpenEEmeter technical working group. The origin of our relationship with LF Energy was really a combination of the OpenEEmeter and CalTRACK, which were being worked on kind of side by side, and when we originally developed them at Recurve, at Open Energy Efficiency, I should say, we had, you know, open sourced them under a fairly permissive license, but we didn't really know what to do with that, and we felt like it was really important for this industry generally to move towards more open standards, to be able to create measurement and verification protocols and software that anybody could use, so that, you know, the work that's getting done to track the impacts of, you know, demand side energy resources can be both understood as well as utilized by, you know, lots of different types of organizations. But as hard as we, you know, tried to kind of wrap our heads around this, and we went and we talked to other organizations that might help with, like NASIO, we had conversations with, and a few others. We really didn't, we were kind of at sea, trying to figure out what to do with all of this. And we met Shulie, who had recently spun up this side project of the Linux Foundation, which is the largest repository of open source software in the world. And she said, well, I've got this idea that maybe we can do for energy what we did for other industries like telecommunications, like the internet, that, you know, the infrastructure that we use to communicate with each other over the internet is built on open source protocols and tools, and it was democratizing. It, you know, opened up information sharing to the globe in a way that was unprecedented. The scope and enormity of the challenge that we face in the energy space seem similar, and the challenges that we face seem similar, that there was a lot of proprietary tools. We face, you know, utilities that are, you know, not so readily willing to give up their control over, you know, core pieces of information. And she said, you know, we've had this idea that maybe we can build software, maybe we can build protocols that transform the energy space, just like we did with these other industries. And so she invited OpenEEmeter and CalTRACK to be part of the inaugural set of 6 projects that would be part of the LF Energy ecosystem. And more importantly than that, she gave us kind of this like North Star that we could then start to follow, where we were, you know, contributing in an important way to a larger project, that the work that so often we look around, you know, at our little corner of the world, and it's the same 20 of us, show up faithfully trying to figure this stuff out. But being part of LF Energy, being part of this bigger vision, allowed us to think about what we were doing in a grander sense, that we were working towards something bigger. And as the work that we did became, more well distilled, it became operationalized within, programs. Being able to point to the broader work of LF Energy as, the kind of again, kind of North Star of what we were doing, really helped to provide the confidence that regulators needed, that governments needed, that helps to put this kind of stuff into the IRA, for example. And so sadly, last summer, Shulie was diagnosed with cancer and was really aggressive. And as so many of us have had, friends, relatives, family members, colleagues face similar challenges, it got the better of Shulie, and she passed away shortly after New Year's this year. And frankly, has left a huge void in this world of somebody tirelessly working to promote this type of work, and articulate the impact that it can have for the bigger things that we're trying to accomplish. I'm on the board of directors now of LF Energy, having been elected by peer organizations to represent us as kind of small at-large members at the board level. And I can speak specifically to, that the organization has really, responded in a really good way to her passing. There's some interim leadership that has stepped forward that really has the right idea in mind. And I feel really good about the future of LF Energy as, again, sort of the home for a lot of this kind of work and to provide meaning for the work that we're doing. But also, at the same time, it's a good chance for us to pause and take a moment to reflect on the people like Shulie who take on these leadership roles, who have an outsized influence on what we do in our lives. The Linux Foundation has put together a couple of different resources that allow those of you who can appreciate this or who knew Shulie personally to write a testimonial. In typical Linux Foundation form, you have to do it in like a GitHub commit, which, if you need help, Phil will help you figure out how to do that. But any of us can also go into the memorial donation section and make a contribution to the work of LF Energy in recognition and respect for Shulie's contributions to the organization. And I think, maybe we just take a moment of silence here. Think about the people who are impactful in our lives. Think about each other. All of the work that we do together, we may not all be part of the same organization, but we're on the same side of the fight here. And just take a minute to appreciate the fact that we're all in this together and we're fighting a good fight. And we're going to miss the people who leave us. But at the same time, one of the last conversations I had with Shulie was, she's like, "Don't you assholes give up on this now." And so, make sure that we, don't step back in our efforts, that we don't retreat from the challenges that are ahead of us. It's this work that we're doing is only going to get more important as we move forward. And so just keep her in mind as we go out and continue to fight towards the ideals that she espoused. So thanks, Adam, for giving me a few minutes, and maybe we just take a moment of silence here.
Thanks, McGee. And just on a personal note myself, I feel like one of the things that makes me excited to come to work every day is the ability to do something that doesn't just benefit one company, but can actually be put out there in a way that can be leveraged by many. And, I think in the demand side world, we're working with all these programs that have been sort of restricted for a long time because they can't really compete on like supply side scale. And I think one of our premises has been for a long time that we can have methods that maybe not everybody loves and agrees on every single like element of them, but we can sort of iterate collectively and make them better. That we can say, look, here's what you can take into the supply side world, and we can take our industry and kind of elevate it in that way. And this is at least to us like a key component of that. And I think when you look at, I just went to the Linux Foundation Energy website today. McGee mentioned that there were 6 original projects, and obviously there are many more now, and they span a much wider variety of technical areas. So we're just kind of one little logo in this much bigger journey of open source and standards and things like this. And all I can say is, if I could look at my own career and could see something like this in the rearview mirror, I'd be very proud of that. So I hope Shulie felt the same way. And without further ado, let's get into the meat of it. And I do want to say that with my screen sharing right now, I can't see any hands raised or anything like that. So if you have a question while I'm kind of going at it here for the next 15 minutes, just interject. Don't worry about interrupting. The whole goal of this working group is ultimately not for us to just be kind of talking at everybody, but it is to conjure some discussion and get ideas and feedback. And in this brief review, I want to tie together a number of elements that we've talked about a number of times already, but to try to paint like a cohesive picture of sort of how we're going about some of this research and some of the model development, and the kinds of things we're grappling with and trying to balance. And I think in our own minds, a lot of what I'm going to talk about has actually become a lot more clear over the last 3 or 4 weeks as we've started to see some actual results. And it has kind of reinforced some of the value of the methodological like framework that we're putting in place in order to get a handle on how things are performing. So we've talked about this many times at this point, but we have these known sources of bias in the CalTRACK 2.0 daily model. Weekend, weekday, seasonal, thermal lag, and some of the functional form components of the model where you have to have linear components and you don't have a sort of a transition in between linear regions. And as we've compared the model fit to actual consumption across thousands of meters, we've seen some different patterns emerge on electric meters versus gas meters as an example. But these components are, if we can solve these components, then the model is something that we will be a more robust fit across most kinds of customers and most kinds of meters. And the solutions we're putting in place or investigating, I should say, are listed on the right-hand side, and they're connected directly to each of these sources of bias. And they're not fancy necessarily. Some of the implementation details, I think, are worth talking about, and they're clever in their own right. But if I were to say to you, well, we have weekend, weekday bias in a model, so we're going to allow the model a flag to be aware of weekends and weekdays, that'd be a very sort of natural thing to do. And that's effectively what we're doing for weekend, weekdays, and seasonal bias. And with thermal lag, we've tried a few things out with thermal lag, and we'll talk about how that's looking today, as well as different thoughts we have about where that might want to go. And I think that's an area we're going to want to get some feedback on, just to not to get too far ahead of ourselves. But the thermal lag stuff, I think there's opportunity for improvement there. And then this restriction to linear functions, just allowing there to be a smooth transition between regions of the model. So if we go, for instance, from a temperature independent region to a linearly temperature increasing region, then oftentimes we have seen very directly that the model ends up trying to balance a nonlinear set of data with a linear model. And so you end up suffering close to the balance point temperature, and you end up suffering the further away from the balance point temperature you get. So allowing the model a smooth transition between the temperature independent region and the temperature dependent regions has been something that we're investigating. Now, here's the problem. As soon as you do all of these things, if you take the existing CalTRACK 2.0 model, there are a maximum number of 5 fitting parameters that can be brought to bear in the fit of a set of daily data. And those are the intercept, the heating and cooling balance points, and the slopes associated with the temperature dependent regions of the model. And all of these solutions that we're investigating ultimately require the addition of parameters to the model. So when we're talking about weekdays and weekends, what we're really saying is, okay, the model was unaware of weekdays and weekends. It was having to split the difference between weekends and weekdays. So in order to remedy that, now we're going to fit essentially 2 distinct models, one on weekdays and one on weekends. And for many, many buildings, think about an office building as an example, where you have 9 to 5, occupancy of the building during weekdays, but on the weekends, everybody's at home. That's like an obvious case where weekend, weekday splitting would be very beneficial to a model. Seasons, so allowing the model to split by seasons, summer, shoulder, and winter is what we've been investigating. Well, now there's more parameters that have to be added. And then when we're talking about thermal bias or thermal inertia or thermal lag, whatever you want to call it, we've been investigating basically a 2-parameter solution to that. And then allowing for the model to have a smooth transition between the temperature independent region and the temperature dependent regions. Well, once again, right, there's additional parameters you have to add to the model. So overall, when you think about how many parameters you could feasibly wind up with, and this is a maximum, it's an upper bound, but nonetheless, there is a possibility under this kind of a formulation to have 54 parameters in a CalTRACK 2.1 model, at least the preliminary formulation that we've been testing. Now, that's most of the time, you're not going to actually end up with 54 parameters in the way we've formulated it, and we can talk more about that. But the upshot is that you have 365 data points, and 54 parameters is begging for overfitting. And so when we talk about overfitting, what do I mean by that? Well, this was an example I walked through a couple weeks ago, and it's essentially saying when we look at model parameters, the right-hand graph shows you as you go from 1 all the way up to roughly 56 model parameters. I erased my x-axis by accident here, but as you go further and further down the rabbit hole of just adding parameters to a model, this is just one example of 1 meter in just a simple linear regression. But you can see that the red dotted line here is the training data set. And so we're looking at the model that was produced on the training data and how it is performing on the training data. You consistently get improvement. So you just improve, and you basically never run into a situation where you're saying to yourself, wow, if I don't just chuck more models in the parameter or chuck more parameters in the model, you always get improvement. But the reality is you're not actually improving the model at some point. At some point, you're actually making the model worse because you're starting to fit the noise, and you're starting to fit underlying patterns that are essentially fooling you, that are not emblematic of the way the building is actually using energy. So you see when we take this model at each one of these steps, where we're just increasing the number of parameters every step of the way, then at some point, if you break out a test data set and you say, we're going to use this as independent verification for how well the model is performing on new data, then you can see the model actually starts to get worse, even though you've made it more complex. And the hope would be because it's more complex, it will do a better job. You actually get to a point where that's actually the opposite happens. So this is what's called overfitting. And in this graph, you can see, there's clearly a region where if we add a bit more complexity to the model, we can reduce our mean squared error. And those middle points of the graph are sort of that sweet spot. But then when you start to see this like real digression between the training and testing sets, and you start to see worse performance, even though the model is getting more complex, well, that's a sure sign that you're overfitting the model. So the way that we're going about gauging and like basically assessing the degree to which a model is overfit is through a procedure called cross-validation, where we take the baseline data, in this case, that's sort of represented by this big blue bar. So think of that big blue bar as 365 data points in the baseline. And then we're splitting it into what are called folds. And I'm just showing an example here. And this is a simplified example, but we've split this into equal sized folds. There are 5 of them. So each one of these folds would have 72 data points. And the rest of the data then is in the remaining folds. And you can cycle through in this kind of way where you can say, okay, fold 1 is going to take its turn as the test data, and the remaining folds are going to be the training data. And we're going to produce a model on the green folds that we then apply to the test data, and we're going to gauge the performance of that model on the test data. And then we cycle through, and every single fold takes its turn as the test sample. And this type of approach, this cross-validation approach, is often considered a best practice in order to make sure that you're not fooling yourself with model performance that is only gauged on a training sample with respect to the training model itself. So this framework is embedded in how we are assessing the model, the preliminary or the candidate models. And as soon as you go from a model that has 5 parameters or even fewer in CalTRACK 2.0, and we're trying to remedy all these sources of bias, we need to be paying close attention to whether or not we're introducing just too many parameters. And if so, where do we need to be actually dialing things back and reaching that balance point of having a model that's not overfit or underfit. But there are also other considerations here that Travis will talk about. And we have to remember that the CalTRACK daily model has specific problems that we're trying to solve. We want to solve seasonal bias. So there may be a situation where we sort of, and this is an area where I think we'd like to present some data in due time to this group of people that shows very definitively the degree of overfitting, but also compares that to the ability of the model to remedy some of these sources of bias. So it is possible, for example, that we have to actually accept some degree of overfitting in order to solve the seasonal bias problem. But to what degree should we accept overfitting? What is the contour of that landscape? That's something we don't quite know yet. And coming into the next meeting, I think we'd like to have some more information that we can present to people. What I'm trying to do now is just give you a sense of how we feel we should be thinking about this. And ultimately, when we're talking about a cross-validation scheme like this, it's very computationally expensive. So it's something that we can certainly do on a few thousand meters. But as we've talked about before, these models need to be, these models need to be applied at times across literally millions of meters. And so this is probably a bridge too far to implement this kind of scheme, like in the model itself, but it's a great testing framework to allow us to figure out what we actually should be doing with respect to the balance between adding more parameters to the model and worrying about overfitting and solving the problems that we're laying out. So the way that this actually takes place that we're proposing in the final model is through penalization of additional parameters. And the way that this operates is you take all of the possible models that could be developed, and you actually produce sort of an initial version of that model. And you're gauging for each one of those candidate models, is the degree of additional complexity worth it, or is it not? So you're basically saying, I'm going to introduce a penalty term that is going to have to be overcome by enhanced model performance. And if my model doesn't perform better enough to cross that threshold, we're going to stick with a simpler model. And this is essentially like a cost benefit test on additional parameters. And in fact, Travis likes to point this out. It's an empirical, like practical way to get the same impact that you would be getting in a more advanced cross-validation scheme, but doing it in like a live model. So Travis can answer quite a few more questions about this. I just wanted to be clear about the fact that cross-validation right now is a scheme that we're using to ultimately determine how we should go about formulating the penalization within the model such that we're striking the right balance. And when I say striking the right balance, that's up for debate. Like, what is the right balance? And so, like I said, over the next few meetings, one of the things that we really want to draw out of the data and be able to present and get feedback on and ideas on is maybe we wind up in a situation where we say, well, it looks like we can solve seasonal bias, but it's at the expense of having the model actually perform worse on any individual data point on average throughout the course of the year. And maybe that's something we're willing to accept, but we don't know the contour of that landscape yet. So with that being said, Travis, would you like to grab the screen, or would you like me to? I think probably it's best if you grab the screen, or we can stop there and take any quick questions that folks may have or thoughts.
The plan that you described last time to try to do essentially what we're doing for model selection in CalTRACK 2 with the sort of new different degrees of flexibility, is your hope that that might somewhat be able to mitigate some of the overfitting, or is it not going to be possible to know whether we're overfitting in the context of like running an actual live model?
Good question. It's a little bit, it's like sort of a little bit in between those things. The penalization approach, I think, needs to be determined at this stage of the process based on the feedback we would get via cross-validation. And so, but that's something that Travis may be able to shed a little bit more detail on as well.
So there's, as with all things, when you get more and more technical, there's at some point you dig to a level where it's a judgment call. So yes, we can use cross-validation to help guide us towards what the appropriate penalty function is. But if you dig a little further down, then how you determine that what you're using as the metric within the cross-validation could also influence that question and that answer. So no matter what way we go, at some point, we are going to have to make the decision of what we think is the direction that we want to go.
That's fair. And is the cross-validation, the way you're saying it now, makes me question my assumption that cross-validation would have been part of every single meters model run. Are you thinking of it more of a way to validate the approach, and then we won't necessarily need to do that kind of cross-validation to fit the parameters of an individual meters model? Or will we keep using it on an ongoing basis?
So the thought process there is that one of the most critical things that we have to keep in mind is that we want to use this methodology on thousands, millions of meters. So if we're talking about the difference of it takes 10 seconds per meter versus it takes 100 seconds per meter, one of those is tenable and the other one is not.
Totally
So
hear
the approach that we are going with right now is basically that we want to use these really cost-intensive methods of cross-validation to validate our more empirical approach that we want to put in.
Gotcha. So once we use cross-validation to tune the hyperparameters, then we just go back to tuning parameters on individual models and not doing the full cross-validation.
Right. So, for example, what's being shown here is like we can do cross-validation to do this to determine what is the best complexity based on the error, but that means that we have to fit the model 10 times for every single time that we want to look at this, which is whenever there's a possibility of, I think I can't remember if it's 49 or 59 different segmentations or splits. So now it's 490 times that we need to fit, and it takes too long.
Yeah, no, I totally hear you. I mean, the CalTRACK 2.0 I thought was too slow. Like, it was frustrating that it took so long because it meant that typically we'd have to buy a lot of hardware in order to do any kind of large data sets. And that's sort of always been on the list of like, can we find some type of a method for searching the balance point space that, wasn't an exhaustive search, for example. Like, there are a lot of places for improving it. So making it slower is definitely not helpful. So I'm totally with you there. So all right, thank you for just explaining sort of how these pieces are going to happen and through the different steps. That's super helpful.
All right. So let's go on with the show.
It's worth mentioning, and sorry to interrupt here, but it's just worth interjecting, Ethan, that one of the things we've done right out the gate before we even got into testing any meters or anything like this was to essentially rewrite the exhaustive grid search function that is in CalTRACK 2.0. Because if we hadn't done that, then we still wouldn't have a framework that would probably even be testable on anything other than like 10 or 15 meters at a time. So there's a lot of computational efficiency that has already been gained here, which gives us a little bit of a bank to pull from that allows us to do these kinds of model selections out the gate, if that makes sense.
Oh, that's great. I mean, you mentioned 10 seconds, and I was like, it used to be a minute, I thought, to do. I mean, it all depends on CPU time. But so are you doing like a hill climbing or a what? Maybe sorry, maybe I don't want to get too far off track here, but.
Oh, it's okay. This is an interesting subject that I just really haven't had the opportunity to talk about, so I'm happy to. So the approach that I took was absolute no to the exhaustive search. Like, I think it was 1 degree that it was searching for everything. That's where the entire cost almost of CalTRACK 2.0 is. So instead of doing that, I am using a global optimization method for both sides and for a single data point. So the global optimization is necessary because there is it's not a convex problem. We can't just rely on downhill or uphill simplex methods or gradient descent or whatever. There's the response surface is a lot more complex. So what we have to do basically is to try to probe that surface with global optimization routines in order to get a pretty good guess of where those breakpoints are. And then once we know where the breakpoints are roughly, then we can go about going in and optimizing the other variables more rigorously using downhill descent methods, as well as then refitting those breakpoint methods. But now we're refitting them hopefully within the global minima as opposed to just picking a random point.
Gotcha. And just a more general question: are you guys pushing these changes up to a new branch on GitHub?
Not as of yet.
When the time is right. Yeah, all the stuff, Ethan, right now is just kind of living in notebooks. So the answer is yes. Like, this stuff will be all part of the open source, release.
Okay.
I have a comment on that though, Ethan. I actually just put a pull request in EEmeter and EEweather to do nothing more than just fix the build, so that it uses kind of the new Pythons for builds and kind of fixes all the requirements and like all the dependencies and all that stuff. So I was going to bring it up later, but there's pull requests out there on both EEmeter and EEweather for kind of preparing for any sort of changes that people might want to make to those two things, because it was in Python 3.6 and like half the dependencies wouldn't even compile and stuff like that. So yeah.
Thanks, Steve. Yeah, that's good. Thanks for bringing that up. I wasn't even aware of that. Yeah. And one thing to note here as well, it's not like we implemented this new set of optimization procedures without checking that we were getting almost identical results to CalTRACK 2.0. Basically, we're getting almost identical results to CalTRACK 2.0. So we've looked at many meters, and this is indeed reproducing CalTRACK 2.0, virtually every time, almost identically.
And it's also found a couple of instances where it fits better. So there's obviously a distribution about what it fits CalTRACK 2.0. So in some cases it's ever so slightly worse, and in other cases it's ever so slightly better. So it's kind of a mixed bag, and overall it is the same, except at a fraction of the time that it takes to actually compute it, which is why we can do all of these additional, more complex things. It was basically that was step one. Like, we needed to basically buy time so that we could spend it elsewhere. All right, so I will move on with the review. So just to help everybody understand on how these splits are working, what I'm showing here on y-axis is energy usage, on x-axis is temperature. So if these are not real meters, these are just characterizations. But to give you an idea, imagine that winter, your data was distributed like this: shoulder and summer. Now, the previous way that CalTRACK 2 would approach this is it would be this gray line right here, where it kind of just splits the difference between all of them. Now, if we were, as humans looking at this, we would say, oh, okay, well, it makes sense to have 3 different models here where we're going to fit one to winter, one to shoulder, and one to summer. So that is effectively what we're doing. And the same thing applies for weekend, weekday splits, as I'm showing here. So if you imagine that the weekdays are these lower point weekends, no, probably the weekends would be the lower points. So the weekends at the lower points and the weekdays at the higher points. Currently, it would try to split the difference. I'm suggesting that we move to a model where it actually fits them independently. But as Adam was pointing out, this adds a lot of parameters, and we have to figure out how we're going to go about figuring, like, we obviously don't want to fit the most complex model to every single one of these individually. So how do we determine what is the appropriate model to fit? Not only that, but how do we know what is the appropriate number of splits in order to get that makes sense? So Adam gave a little bit of a preview, but for the model selection criteria, we are currently using like an AIC corrected sample adjusted BIC for those that are interested in what these random acronyms mean. AIC is a Kaike information criterion. BIC is Bayesian information criterion. There are also some more complex versions of these information and selection criterion. It's kind of a gradient. So at one end you have AIC and BIC, and then as you get more and more complex, you get closer and closer to both the cost and the accuracy of cross-validation. So I think we want to kind of sit in this AIC BIC range and not go the next step of these DIC widely acceptable information criterion and Watanabe Bayesian information criterion, because these you start having to do multiple fits, and it just that cost starts to increase. Another one that we are now entertaining that I'll talk about much later is our own empirical fitting algorithm. And in general, the way that these work is by minimizing the error and by penalizing by the number of coefficients. And I think that Adam's description of it as being a cost-benefit analysis is just dead on perfect. Does the benefit of additional coefficients basically end up with, or sorry, the cost of additional coefficients match up with the benefit that you get in minimizing the error. So I'm going to just refer back to this because this is telling us that we have a maximum of 54 parameters and we have 365 days in a year. If we were to actually fit 365 days to 54 parameters, I cannot imagine how that would not be massively overfit unless the models were, it would probably be the strangest meter that you had ever looked at. It's just not going to happen. So these are for those of you that are more mathematically inclined, these are the selection criterion equations. So to describe what's going on here, N is the number of data points or days. If you combine that, which is going to be a constant, with the natural log of 2 pi, which is also a constant. So effectively the only, can you guys see my mouse? Just curious.
Yes.
Perfect.
It's kind of faint.
Okay. All right. So effectively, the only thing that really changes in this negative log likelihood function is this this loss value, because this loss value is going to be decreasing as you increase the number of coefficients. So then this negative log likelihood function is the basis of AIC, BIC, and this is sample adjusted BIC. So the first term here is exactly the same. The term that is the penalization term is this 2k, k log n, and so forth. So what's happening is we are basically increasing the cost, or the total value of the function here by some function of k, which is the number of predictors, it's the number of parameters, plus some split penalty. The split penalty is necessary because now whenever we're talking about, let's in the simple case talk about just doing weekday weekend. So for the weekday model, there's going to be, let's say at maximum seven parameters. And on the weekend, let's say it's temperature independent. So you just have a single coefficient to describe what's happening. Well, we sum all of those up, so you end up with 8. But you also want to penalize the function for having segmented your data at all. So there's also the split penalty. If you go into the literature, segmenting your data like this and having some sort of a split penalty is not a common thing, not as common as you might think. And so there's no really agreed upon way to set the split penalty. Currently, what I have everything set to is 1 for every split, which is, that's kind of makes intuitive sense as well, because you're basically describing the split with one coefficient. So, and by the way, these reviews is really important so that I can explain, so that you'll understand what the different models and permutations that I've looked at are actually testing. So on to thermal lag. The way that I'm approaching thermal lag is, imagine, hold on, what is it? You know what? Armin, tell me if I need to respond to that.
Yeah.
Otherwise, you got it.
Greg, let's come back to that question. We'll stay on the line and we'll come back to that question. It's a great question.
Okay. All right. So the current way that I've implemented thermal lag is, imagine that we're saying what the temperature of the current day is. Well, right now we would just average all of the temperatures in the 24 hours. Well, one way that we could approach thermal lag would be, well, we have this offset value, mu, and then we have another term to describe the range that we want to look at. So if we wanted to have, what is this, a 36-hour delay, then mu would be 36, and then sigma, if we wanted to delay it by 1 day, would be 12. This is a really flexible way of implementing it, because we can describe a lag time, we can also have a lead time because we allow mu to be from -3 to 3 days, and then we allow sigma to be between 0.5, which would be 1 day, because remember it's 2 times that, to 3 days, which is to say, with this formulation, we can describe no lag at all. We can describe a lead time. We can describe a 36-hour delay or lag time. We have lots of options. It's very flexible. Next up, we have the adaptive loss function. This one might be a little bit more controversial, but I'm just going to go ahead and say this initially. This is kind of now getting to the idea of where we need to decide what the purpose of this model is. But before we jump to that, let's just look at the numbers that show up a little bit later on in the results, just so that you understand how it's working, not its merit. Let's go ahead and describe that. So here on the top left plot is the loss response, and this is on the x-axis is the number of standard deviations from the mean. So what this is basically saying is if we go with the sum of squared errors, it is actually the lowest possible loss response that we can get. The highest loss response is the Welsh loss function, which is shown here in purple. However, if you were to pick the Welsh loss function, then the entire thing is raised higher, and that's the penalty you pay for decreasing these outliers. So what we do is we fit, because this is a continuous function, and these are just simply alpha values that I have picked out. So what we do is we do an optimization to figure out what is the proper or the best alpha to balance this this out, since now we have two ranges, or two extremes rather, between sum of squared error and the Welsh loss function. Once we know what that optimal alpha is, then we can transform that into what the weight should be for our sum of squared errors. And when I say sum of squared errors, it's a weighted sum of squared errors at this point. So if we actually, the alpha picks sum of squared errors, then the weight is simply 1 across the board. Or we can go with like a smoothed L1, a Cauchy function, Germain McClure, Welsh, and we would get these sort of weights depending on the distance, the standard deviation from the mean. Now, that's a whole bunch of technical details of how it's working underneath the hood, but how should, just really simply, how should it work? Well, that brings us to this plot where I show the energy usage again against temperature with just fake data. So imagine for a moment that we have that data, but then these are the 7 data points at which the house actually just shut off their power because they were having some electrician do some electrical work. So they have 0 consumption on these days. The current way that the model would fit that would be to try to split the difference, and instead of fitting the behavior of the household, it would try to fit the entire amount of data, so then you end up a little bit lower than you would expect. However, if we downweight these points, we end up with something that describes the more typical usage behavior of the building. All right.
Yeah, so I think now is a good time to break, and let's just chat about Greg's question quickly. And Travis, if you don't mind, I put a couple slides in the appendix, slides 31 and 32, that we can hit quickly.
Okay.
Assuming that your slides updated, in which they did. Greg. Okay, so great. Greg, good question. The question for everybody who hasn't read the chat is essentially, why do we need a differentiation between season in the model? Why is it not just a temperature coefficient, and a 60-degree day in March should be treated like a 60-degree day in April, should be treated like a 60-degree day in January, and so forth? And the answer is we observe different behavior for that 60-degree day in each of the seasons. And you can see that in this graph, where on the right-hand side with the blue data, this is the difference between the model and the actual consumption during the winter time for a whole bunch of gas meters, versus the summer in red and the shoulder in green. And if you just look at those lower panels, these are the aggregation of something like 85,000 gas meters. And the model prediction is just a baseline model fit on the data. It's not even a counterfactual. It's just a baseline model fit is shown in the solid line. And the actual observed data is shown in the data points themselves, the triangles, if you're looking at the winter. And you can see these distinct error patterns that arise in the upper panels. So winter, shoulder, summer, all have these very different error patterns. And over the course of a year, the model sort of balances itself out, and bias is very close to zero. But in any given season, because people have different behavior with respect to any given temperature, you know, in the winter, what is it that we're seeing? Well, we're seeing the model is under predicting around the balance point temperature. That basically means that people they're actually heating their homes around that balance point temperature much more than they actually are in the summer. So this is the reason why, and this is not a small effect. When we're talking about seasonal bias, when we look at these very same meters and we look at percent bias, it's like 14% bias in the winter. So on out, you know, like the collective, the average daily data point in the winter is 14% too high relative to the model. And the opposite effect is true for the summer and the shoulder periods. And if you go to the next slide, this is just to say, this is not a tail of the distribution type of effect. This is a systematic effect that is exhibited amongst most customers. So I'm showing the winter here. This is just bias in the winter. And if you go to the next slide, it's bias in the summer. And it's like completely opposite. So, but in each case, it's systematic. So this is one of the things that, you know, we've observed in sort of diagnosing where there's an opportunity for improvement in CalTRACK 2.0. And what Travis is going to talk about right now are the actual some of the actual results from allowing the model to split. And like I said earlier, there's room for improvement here still, I believe, but we're seeing some promising signs. So Travis, with that said, back to you.
Ethan has a question on what is this data?
Ethan, let me reach out to you later. I think we're close to being able to just say what the data set is, but we're looking for one more sort of hurdle that we got to cross in order to say that. It's residential gas data.
Go ahead, Greg.
Yeah, just to follow up, and I don't want to take too much time on this, but I guess part of what I was getting at is, you know, how much of this sort of seasonal accounting is explaining variance that is, you know, weather-related stuff that's inducing certain behaviors that's not currently included, whether you're talking about insolation, you know, or the number of sun hours a day, or humidity, or, you know, even like sort of longer-term thermal lag. You were talking about fall versus spring, or, you know, as Ethan mentioned, things that are not related to weather, but just sort of how we've organized ourselves socially, right? So similar to like the weekday split, we've decided, you know, 9 to 5 is kind of like a normal whatever. You know, kids go to school in the winter. That's what we've decided. So just trying to suss out, like, you know, is there benefit to maybe including parameters that are not so much a composite, but are actually sort of based in something that's, you know, actually explainable, if that kind of makes sense.
Well, so yeah, I have two comments on that, and Travis, feel free to jump in as well. But comment number one is I don't think that what we're seeing here is unexplainable. I think it makes a lot of sense, actually. You know, when you have a winter day, the days are shorter, and a 60-degree day, you know, 60-degree average temperature day probably has a number of cold hours, especially in the morning, and you need to heat your home. Whereas a 60-degree day in the summer, it may be a relief to you. You know, you probably welcome it. And the need to heat your home probably is not as severe. And with respect to the concept of like, well, maybe there are other parameters that we should bring to bear, you know, maybe there's like school year seasons, or, you know, there's other kinds of like human behavior, or just like patterns in human movement and things like that. I guess to me, most of the time, those things, keep in mind, we're modeling individual meters. So if we allow for a seasonal split, we're going to inherently capture those things. And we're going to do so in a way that can be applied across all meters. I guess what I would ask the folks on this call, or you, if you've thought about this, are what types of parameters would you be confident would actually be incorporable into a model like this that would be representative of nearly all meters, because that's the model has to be extensible.
And to add to that, we also have to keep in mind, like, what is the application for the model that we're building? Because if it were an engineering model, then yeah, we could add individual things like, do they have kids? Do they go to school? What school do they go to? Like, we could go very detailed. But the problem is, that's not the purpose of these models. These models, like, we model individual meters, but we do so, like I mentioned earlier, with thousands, millions of meters, where it's just infeasible to have all of that information.
But it's a totally fair question. It's like it's a good comment. Like,
oops.
And then maybe there are elements that we could incorporate that would actually capture or like entail these effects more so than the season itself. So if you have ideas, like, definitely willing to, but all I think we're really saying here is, keep in mind the generalizability that these models need to, allow for.
Thank you.
Cool.
As far as Ethan, your comment about clustering weekday, weekend, and that sort of thing, like, totally open to doing something like that. It's more of an issue of, is the development time going to be worth it versus us specifically saying, okay, weekends are Saturdays and Sundays. If we find that like 98% of meters basically follow that, then us putting that assumption into the model is not going to be too much worse than something that's a little more complex. So it's always a balance of complexity of what we want to compute versus the benefit we'll get. And you might be totally right, and that's worth it. It's just something that we haven't explored yet. And the same thing applies, by the way, for seasons. I don't want to show that yet. I actually have a way of determining season based off of temperature, so that you wouldn't have to specify what the season is. It's something that we might be interested in implementing, but so far it's just been kind of a little couple-hour side project that I did. And yes, Greg, thermal lag can't really be implemented, because can be implemented, but it can't be implemented. That's not something that we do on a population level. Humidity, definitely. Insulation changes every single house, so there's really no way to get that data. But something like humidity could definitely be important. Cloud coverage or GHI, like solar irradiance, all of that could matter, and that's things that those are parameters and information that we could get from a broad source. So all of those things are open season. Oh, I'm sorry. I thought that was a typo. Yeah. You were dead on. Okay, so let's jump into some results. And to start with, these are on gas residential meters from the same set that I just showed, but though a subset of those. The thing to note here is that I'm going to be showing these plots a lot. So I'm going to go ahead and explain what you should be looking at and what means what. So on the y-axis is the improvement over CalTRACK 2.0. This is done as a percentage. So basically, we look at the error, of the current model, so sum of squared errors of CalTRACK 2.0 or 2.1, subtract CalTRACK 2.0, whatever its error was, divide the result of that by CalTRACK 2.0, multiply by 100. That gives us an information on how much better or worse it is. On the x-axis here, I have all of the different models that I have looked at and compared to CalTRACK 2.0. So I have sum of squared errors. Sum of squared errors where I'm only looking at basic models. This is to say I am excluding the model where I allow that smoothing term to be put in. I also am looking at sum of squared errors where I exclude the ability for it to have a weekend split. And I also do the same thing for to exclude seasonal splits. Now, we kind of have a break here where this one is now showing an L1 loss. An L1 loss is basically you're just looking at the residuals and take the absolute of that and sum all of that up. And then this is the adaptive loss function implemented. These last two plots are the sum of squared errors where I'm allowing thermal lag, and then this last one is the adaptive loss function where I'm showing the thermal lag. So now getting into what are these crazy shapes that are on the screen. So if you split this down the middle, what you're seeing is a distribution of the improvement over CalTRACK 2.0, and this is a smooth distribution. So kernel density estimation, really. The white dot here is the median value, and this black line represents the upper and lower 25% bounds. So the 25% quantile and the 75% quantile. Okay, a lot of background knowledge to understanding these plots, but now we can kind of dig into what they're showing. So basically, if we compare sum of squared errors for all of the models versus the CalTRACK 2.0, the vast majority of the time we have a distribution about 0. And that is just telling us basically that we are more or less returning back CalTRACK 2.0. That is basically the same for basic models and weekend, weekday splits. What does that indicate to us? That is indicative that having a weekend split is basically not important for these gas residential meters. However, no season split is basically the same, like even closer to 0. So this is that excluding the seasonal split is actually detrimental, because now we are returning back CalTRACK 2.0 almost exactly. The L1 loss function is ever so slightly worse, and the adaptive loss function is like maybe 0.3% worse. If you look at this distribution, however, it could be argued that both of these, if you were to factor in uncertainty, is basically the same. The thermal lag, on the other hand, is substantially worse, though just to cut ahead a little bit, that's not always the case. Now, the thing of interest here is that only 101 meters out of 4,911 were actually given a split. And this was all calculated with an AIC to determine the number of splits, with a penalty for segmentation at 1 times the number of splits. So almost all of these that I'm showing right here only have a single split. However, once we do split these meters, we are seeing significant improvement in the model, where for sum of squared errors, it's nearly a 25% increase, up to probably 30-35% on the high end. And we have nothing that is actually worse than CalTRACK 2.0. Again, if we exclude the season split, though, which tells us that everything that we're seeing here is basically a season split, we get CalTRACK 2.0 right back. Now, looking at the L1 and adaptive loss function both together, the thing to note here is that the median is basically the same, except the quantiles are a bit tighter. And what this tells me is that when you're looking at this, you can basically expect for there to be more improvement on average with the adaptive and L1 loss functions as opposed to the sum of squared errors and the model. The cost that you pay is that occasionally it is a little bit worse, like 5% worse. But again, vast majority of the time it is improvement. Most of the time I'm just going to skip talking about thermal lag because it's pretty clear that it is showing up worse right now. And by the way, if anybody has another comment that they would like to make or a question about these, please just jump in. Until then, though, I'm just going to assume that everybody is enjoying the show and continue on. So now I'm looking at the split or the models that had no splits. And this is interesting because this is basically saying, like, before there was a little bit of difference here, but once we get rid of all of those, it returns back, again, basically CalTRACK 2.0. Whereas here, again, it's basically the same plot. It almost looks exactly the same, and that is mostly because there's only a 2% difference. Yeah, the reason for this is basically that. So I've done some preliminary testing, and even if I reduce the penalization, the additional penalization to 0, it still basically picks these same exact meters out, and it's doing that because of the AIC choice. So that's why we are now thinking, okay, maybe we as the experts in this domain, we know that there's probably a decent chance that a model might actually be different in the summer, shoulder, or winter, but the AIC doesn't know that. It's judging entirely based off of, does the improvement justify the additional cost? So maybe what we need to do, basically repeating what Adam said earlier, is maybe we are willing to accept a little bit higher bias in order to and to also have maybe we want a lower bias and a higher uncertainty so that we do not have as much seasonal bias.
Ethan, yeah, what are your thoughts?
Oh, sorry, missed that.
Well, so just one aside thought is that we could potentially, instead of using calendar months for the seasons, do essentially some kind of a clustering on, heating and cooling periods to find contiguous periods that are, predominantly heating, cooling, and shoulder. I haven't looked at the data to see like how messy that is. And obviously we have all the same problems of like not wanting to have erratic results. But my big question is just looking at the thermal lag on like how much worse than CalTRACK 2.0 these got is, I thought from your description, I understood that it was adaptively choosing those mu and sigma values to figure out like how much searching and how big a lag period and stuff like that in order to optimize the model. And what I'm trying to understand is if what we're comparing here between this, potential improvement, quote unquote, and CalTRACK 2.0, that we're comparing the like CVRMSE and stuff that are the same parameters that are being optimized. If all these homes do worse with the thermal lag, why didn't the model choose mu and sigma values that are 0 or whatever essentially says no thermal lag? Like, how could it ever be worse?
Yeah, can I jump in there quick with point 1, Travis? And I'll hand the baton to you for point 2. We've talked a lot about this, and it's a great question. Number 1, keep in mind that all of these results are showing you the statistics that were determined based on using the training model on the testing data. So there's an element of overfitting here.
Okay.
And this is exactly why cross-validation is such an important tool. But it's beyond that, I think. And Travis, yeah, feel free to explain our other probably even more important point here.
Wait, sorry, Adam. So let me just make sure that I understand the training versus testing. So like this is the error from the training model on the testing data set. Is the comparison against CalTRACK 2.0 also a version of CalTRACK 2.0 that's done with the cross validation? So it's training CalTRACK 2.0, with a reserve set and then calculating the error on that? Or is it comparing the error that CalTRACK 2.0 gets when it's allowed to overfit and get credit for overfitting with your more stringent?
Keep in mind that CalTRACK 2.0 is what it is. You know,
it is what it is, but it's a totally different test if we're comparing the CVRMSE that CalTRACK 2.0 gets when trained and tested on the same set
Yes,
as we
yes,
would get
you are,
if the algorithm is trained and tested on a reserve.
you are absolutely correct. And the CalTRACK 2.0 that I am describing is actually the CalTRACK 2.1 implementation of CalTRACK 2.0. So it is all of the speed improvements that I've put in, and I've tested so that it basically always returns back CalTRACK 2.0 results. So now I have that implementation. So I do the same exact test and train sets for CalTRACK 2.0, and I am directly comparing those for each of these methods. So it is an apples to apples comparison.
Thank you.
good point, Ethan.
Yes.
Yeah.
Okay. And as far as the test train split, I apologize. I forgot to explain that part of these plots. So what these are is actually a tenfold cross-validation, and this is the average RMSE of those 10 test train splits, where I am looking at the results from the test data. So this is information that is being derived having never been fit to this data. With that being said, you are also correct in that what is happening is that, yes, in theory, if there is no thermal lag, it can return back a mu of 0 and a sigma of 12, which would be an average for the current day. But there's two things going on. One is with the test train split that Adam just mentioned. The other is that so far in my implementation of this, I have been treating that as a separate step from the model selection criteria. And I realized actually earlier today that I should really be including these two variables in that model selection criteria, because there's always the possibility that even though it does not pick 0 and 12, those are still fitting parameters that I'm including, and there might be no justification for including those. So I actually put that inside of my model selection criteria so that I can then reject it if it's not an improvement, in which case I think that the results that we're seeing here would be significantly different. And I'm also, there's two more things. One, there's always the possibility of bugs. I can honestly tell you that I already found one with the thermal lag, and so this looks actually better than it used to, even though it looks pretty bad. The other point is that I'm also, maybe this imagination of or creation of what thermal lag is, maybe it's a problem of implementation. Maybe there is a better way to implement thermal lag rather than what I am doing. I chose this specifically because it keeps the model as it is and allows us to break apart heating and cooling load rather easily, but maybe there is a different, better way.
This is Ken. Just a couple other things. Is it possible? I'm not as familiar or as experienced with the whole K-fold validation process, but you're trying to understand something that is potentially a much finer grain effect, and you're chopping stuff up so much. Is it possible that, unlike weekday, weekend, and so forth, where where you can get that spread out across all of your folds and so forth, that you're not gonna do as well at picking up something that's just a couple days, because you could very easily be just lacking the data in your training. I guess if you've got 9/10 of the data, that's not going to be an issue.
Yeah, it's 80% of the data. It's an 80-20 split. With that said, though, don't forget it's tenfold. So if, let's say that I am missing all of the days from one of those K-folds, because we do not actually repeat, and it's a shuffled k-fold, those days will be in the other 9 almost guaranteed. So there's never a point at which we don't take those days into consideration. But what you said about them only happening on a few days, I think is a key point to talk about right now, because basically that is saying that the thermal lag does not particularly matter until you have a large temperature gradient. And that's only going to happen on a few days out of the year. So in the end, it's not going to have that large of an effect when you're looking at the aggregated results.
Yeah, I quick comment on this as well. Ken, I don't know if you were getting at this in your question or not, but when we're talking about the splits themselves in the cross-validation procedure, really what we are hiding from our training data are the consumption data points. They're not actually the temperature data points on those days. So we debated this quite a bit and have, long story short, we've confirmed that's a valid way to go about this. So if you have a data point that's been binned into your test sample, you can still allow the thermal lag parameter or the thermal lag formalism to know what the temperature is of that data point. Otherwise, you're just missing data in your model that your model actually needs.
Yeah, I get it. The one other thing on the temperature lags that when we were exploring this years ago didn't get as far as you guys have gotten here, but they don't seem symmetrical. So they have to in the summer, if it's cooler, it's over or under certain temperature criteria, and it doesn't and they're not symmetrical in direction and so forth. And I can't tell quickly enough whether the configuration you've got could handle that. And I'm not sure it's worth it either. I don't know that that's a particularly fruitful direction to go, as I think you're implying here, but
Yeah.
that was just an observation we had years ago.
Yeah, Travis, we have 5 minutes left in the regularly scheduled meeting here. Time really flies. Let me just give a few comments, and then if folks need to run, they can run. And for folks who want to stay, we can stay. So with respect to the thermal lag stuff, I think we're very keen on coming back, not necessarily hitting the reset button, but seeing if in allowing the model to optimize on this, like Travis was talking about, will bear more fruit. I think we're also interested in trying a few different formalisms for this. So if people have ideas on, other ways that you've seen in the past that actually help with this problem, we're also very open to, frankly, just dropping it. Like if thermal lag really isn't that big of a deal, then we can drop it. We have tested for thermal lag bias in CalTRACK 2.0, and it definitely exists. Like it is there. But is it as potentially severe as seasonal bias? Probably not. So given the fact that it is additional parameters and that has the risk of causing overfitting, and it is a little more complex, to be sure, this potentially is something that we can leave by the wayside for this version or permanently. But I think we're still in the relatively early stages of wrapping our heads around that. Now, with respect to like the model in general and kind of where what we're thinking and where we'd like some feedback from folks, Travis, if you don't mind just going back one slide, we have other examples here. Right now we're looking at gas residential, but we also have a few things we can show for folks who can stay on the commercial side and on the electric side. But where I think I'm very encouraged is when you look at this right-hand plot, when the model does split into seasons within the gas sample, it's really, really clear that like we're getting a massive improvement. Now, if we're talking about a sample of 5,000 meters, but we only get 100 that actually get split out, we're not going to solve that systematic bias issue. That just goes without saying. So this is why Travis keeps coming back to this concept of is the AIC implementation of the penalty the right way to go? And so what we've been talking about, like literally a lot of this stuff you're looking at, we just have seen for ourselves for the first time in the last 2 days. And what we're thinking about now is potentially a empirical loss function where we reduce the severity and we give ourselves a vantage point of underfitting versus overfitting and seasonal bias. And that's really kind of this like 3-dimensional landscape that we need to be looking at in order to actually give ourselves collectively the information to ultimately make a judgment call. And it may very well be that in order to really solve the seasonal bias issue, we need to accept some overfitting. And that goes for all of these elements of bias that we're talking about. But to what degree we're willing to accept that is an open question. And I think there may be an obvious answer and there may not be. So, but that's where we'd like to go with some of this in the coming weeks and come back the next time and have that conversation with a little bit more data to present, on that front.
All right. So do we want to continue on for those that want to stay, or shall we cut this and put it at the beginning of the next meeting? That is a question for the audience.
Well, I have a question. I think I need to head out because I'm I'm already half an hour cut into my other meeting. But I'm curious whether you plan for sort of systematically searching. It sounds like that penalty function for the overfitting, right? For the number of parameters, like how much do you charge the model fit for the extra parameters? And it sounds like that's pretty expensive right now. If you took it to 0, presumably, we would be happier with higher parameter models. So I know it's at some level a judgment call, but are you able to like set your code up to do 10 loops of progressively smaller penalties and find some way to visualize like at what point do we start to see any quote unquote improvement, so that we can then start to expertly assess what the cost is on that, and I don't know, right? Because otherwise, at this point, it sort of looks like we walk away, right?
Yeah. So that is exactly the idea that we have right now, and this is kind of what we're thinking right now, and it's basically that we could basically put a percent effectiveness term in front of the penalty function for any of these, and then we can just go for just do a quick search of steps of, I don't know, 5% to 10%, and then we will get back different models, different errors, and then we can kind of see what that looks like on a plot. So that's what we're talking about when we're talking about having an empirical model.
Sounds exciting. That's great. Thank you, and really appreciate all the work that's gone in here. This is stuff we've talked about for years, and it's very exciting to see some real numbers put to it, and certainly appreciate that it's never as easy to actually do it than it was to wave our hands and say, what about thermal lag?
Yeah.
Yeah.
Thanks,
Ken, I wanted to address your last comment, and that is that yes, we absolutely can do this on a seasonal basis with the same exact framework that we have put in. And what it does is it actually picks, I guess I don't have. It actually picks a unique mu and sigma for each of the seasons. However, that is effectively a new model, and it has to be treated as such, which is to say that when I show these plots right here, that these plots, these 101 meters, they all have their own unique mu and sigma for whatever the split they took was.
Travis, before we let everybody go, I think we should show the commercial results because they're fascinating, especially in context of the gas residential. So we'll switch for a second from residential gas to commercial electric. And, you know, I just want to point out one quick thing. And this is another, I think, good sign of where things are going. When we look at the commercial, like we look at this right-hand plot, these are the meters that got split. The left-hand plot, again, like Travis mentioned earlier, are the meters that did not get split. And what we're seeing is, again, dramatic improvement in model performance on the meters that did get split. But where things look very different than the residential gas side is on commercial electric. And this is true also for residential electric. What matters is the weekday bias. So you see that when we don't allow for that weekend split in that right-hand graph, we're really not seeing a lot of improvement. But when we do allow for that weekday split, the next orange bar over from that, we see a substantial improvement. And if we toggle back to the residential results on the gas side, what matters is the seasonal split, not the weekday split. And this is pretty intuitive, right? If you think about commercial electricity, then when you encounter the weekends, a lot of these buildings are, they just shut their doors. And so what actually you would imagine would matter is the weekday, much more so than the season. But on the gas side, we're talking about in a composition of end uses that is much more heavily weighted toward temperature dependent consumption, heating. And so we're like the isolation of heating and the different behavior that we're seeing between seasons really is exacerbated when we're isolating gas consumption. So it's nice to see that these models are reflecting some of that intuitive knowledge that we would presume. That gives me at least a lot of confidence that we're on the right track, but we clearly have quite a bit of tuning to do. And we have a lot more to learn before we have a good understanding of where this is all going to land. So want to thank Travis and Armin. They've been working behind the scenes like crazy hours on all of this. And Ethan, I definitely appreciate some of those kind words around, the effort that it takes to do this. I think next meeting we're going to have, this sets the table, I hope, for us to be able to, add another dimension here. And the more pieces of this puzzle we put together, the more I think we're going to be able to make some clear-eyed decisions about what ultimately should wind up in a final model. And we can start to get to the tail end of some of this. Obviously, we're enthusiastic about CalTRACK hourly as well. And lastly, before I let everybody go, there were a few people who had reached out wanting to understand what the approach in CalTRACK was to delivered fuels. And I'd like for us to carve out a little bit of time to talk about that in the next meeting if possible as well. So just want to acknowledge those folks who reached out on that front. I think it's a really important conversation, especially in the Northeast. And with IRA funds out there, we'd be crazy not to, to just say, oh, well, we can't handle it, right? When there might be something that can work. So want to say thanks to everybody, and we will reach out. I'm thinking that we'll probably go 3 weeks from today. That seems to be a reasonable cadence. Optimism springs eternal the moment we leave the meeting, but then we got to work through code and actually work through testing. So I think 3 weeks will probably give us the ability to have, a more robust data set. And we really appreciate everybody's time here. It's not a cheap meeting for any of us. We're all busy. We all have, really active stuff going on. So with that being said, just want to thank everybody. Super good discussion today. And we will reach out and schedule that next meeting, and we'll look forward to it.